Hi everyone, welcome back to ContextOps. Today we have with us our usual host, Joshua Thomas, and our guest today is Mike. Hey Mike, how are you?
How are you today? Thanks for having me.
I'm good, I'm good. Thank you so much for joining us today. Right now,
My
Mike,
pleasure.
I've been a big follower, big fan of your newsletter on knowledge architecture for I think now over 2 years. I've been a consistent reader. I do have a complaint that we aren't reading much of. you- You've stopped writing more frequently of late.
Yes, we'll get to that.
Yeah, but Mike, I know you've built the economic graph at LinkedIn. You've done some fantastic work at eBay, and now you're building hypergraphs. And that's the LinkedIn bio, right? But why don't you, for our audience, tell us more about how did a computational linguist and a cognitive scientist ended up building knowledge graph at the world's largest social network?
What can I say? Well, linguists and cognitive scientists also need to represent knowledge because that's what they study. So linguists call it meaning. This is how I got started getting interested in these things. And cognitive scientists as well. What I did for my PhD was study what steps people go through, what cognitive operations they make when they're doing simultaneous translation. And for that, they have to use their prior knowledge and access the meaning of the words that they're talking about. So I needed a knowledge graph sort of representation for that as well. So I've been doing knowledge graphs in very different ways for different applications for quite a long time.
Nice, nice, thanks. And tell us a bit more about what you're doing at Hypergraph, because I think I read it somewhere that you're building what is being referred to as an X-ray machine for everyone else's graph.
Mm-hmm.
What does that mean? Tell us more.
So at Hypergraph, we've been focusing on tools for building and now validating knowledge graphs. So I call it an X-ray machine because if you get a large file, the one that comes to mind is Wikidata. They're like 20 billion tuples like that. You look at it, you have no idea what makes sense, what doesn't make sense, if it's covering what you need, if it's consistent. There are a whole bunch of different questions like that. Wikidata was to a great extent built by hand, but now there are so many tools where at a press of a button, you can generate what some people call a knowledge graph. And then the question arises, is it a good one? Is it a useful one? Is it a consistent one? Is it going to do the job that we need it to do? And this is particularly important because we use knowledge graphs as a single source of truth. So much of many of the applications, like the ones that I built at LinkedIn, are based on this foundational layer. But today, we have no idea how good they are, where the gaps are, and where the strengths are. So we're working on tools to build so that we can assess this systematically.
Okay, so there is a lot to unpack and simplify for the audience sake, right? And I'll start with the most simple term, which is knowledge graphs,
Yes.
because know, last 7 months, every AI conference has now at least one panel, one speaker talking about context graphs and knowledge graphs and some version of that. And this wasn't the case 2 years back. 2 years back, I don't think knowledge graphs were so popular. I wish they were so popular. Right? We all wish they would have been more popular. Yeah.
Yes, they're always there. They're just not as present in the press. Put it that way.
Yes. Obviously, the core technology has existed for a very, very long time now. The question becomes, when you describe knowledge graphs, and there are a bunch of technical jargons around this. There is a core term of knowledge graph, taxonomies, ontologies, right? Can you just break these terms down?
Sure.
Because we'll use this over and over again over the next half an hour, 40 minutes. Yeah.
Yeah, so sometimes I use the term knowledge resources to kind of group all of those together. Okay, a taxonomy for me is just a much simplified knowledge graph. it's reduced to only a couple kinds of relations. And then it gets more complex when you go to an ontology, which uses more kinds of relations. And a knowledge graph incorporates both of those and extends it with additional kinds of statements that it can store and exploit. Okay, and these are all collections of statements of the kind, a dog is a kind of mammal. Okay, that's a taxonomy relation, but knowledge graphs have lots of these. A dog has a heart and a stomach, for example. Often we hope that there are additional resources that map those concepts onto words and saying things like dog is the same as a canine, as the same as a pooch, as the same as a mutt, so that we can map between the words that we encounter in user queries, in documents, and the concepts that we want to use to represent the meaning.
Okay. Now, and so I think that's a very simple definition, a simple way to understand those three terms, very helpful. Now, in the context of Gen AI, now obviously graphs and ontologies and taxonomies have existed for the longest time imaginable, right? You also use the word source of truth to describe a knowledge graph. That graphs are what is referred to as a source of truth, right? Can you just explain a bit more on that? Why a graph's the source of truth versus what the more popular vector RAG, which says there are thousands embeddings of chunks of text. Why can't they be a source of truth?
Okay, so a source of truth, when I use the term source of truth, that's the way we use a resource. So we have databases that are a source of truth, for example, regular relational databases. And they're a source of truth in the sense that we use them as the starting point for a range of other processes. And we refer back to them to double check whether the processes are working. Okay? For databases, we do that with data. For knowledge graphs, we do that with knowledge, which is more abstract and more aggregated. Okay? So embeddings are another way of aggregating data, but only based on which things go with which others. So it's correlational or collocational, if you will. So it doesn't represent very explicitly different kinds of relations, like X is a part of Y, okay? Or X is used for Y, or X is a kind of Y. It just says this term shows up very frequently next to these other terms. Okay, so they're qualitatively different kinds of things, and they work well for different kinds of uses. So I'm used to using hybrid systems where we use embeddings as a kind of filtering device to say, oh, okay, we want to do our intensive processing on just this subset of what we have. So embeddings are great for that. They can identify a subspace, as it were, or a subset of relevant items to focus on. But then on top of that, we want to do qualitatively different operations and identify qualitatively different relations. Does that kind of make sense?
It does. It does. Now, this is helpful. We're able to get some of the basics out of the way, right? But
so, Mike, I had a question. So, in this hybrid approach, so people talk about using vectors of chunks, like embeddings of chunks of text, and people talk about using graphs, like whether it's RDF or property graphs. So, what I heard you say seemed to be like something which combines both, which is like
common,
localize using the embedding and then go ahead and traverse the graph. Is that what you were saying?
That's one common approach. Another way of looking at it is graph neural networks, where the graph itself is the input, and then the neural networks can do different operations on the graph. There are a wide range of techniques that are available. Yeah, that's right. You can build embeddings from graph as input. You can train LLMs with graphs as input. It's not very common, but it's possible, and it's been done.
Right.
So the only point I want to make here is that you don't have to choose between one and the other. Each is good for different things.
So now that we have the basics or definitions out of the way, right? Because this is this can get really confusing for a lot of people who are not, who are not knowledge graph first in their approaches, right? So now let's get back to the original question. How do you decide, or how should one decide whether the graph that they've managed to put together, and one of the most popularized approach here is the Microsoft GraphRag, which was open source a few years back, and that sort of put like a big shining lights, spotlights on graphs and so on. I guess my question is very simple: how does one even start? Where does one start to self-diagnose what they have?
So at the moment, that's really difficult. Most people do it manually, and since there are not a lot of people who have specific training in this, it gets confusing and it's difficult to make it work productively, right? So this is why we're focusing on tools now, to make it possible for you to point your graph at a tool, and the tool will tell you something relevant. It will tell you things like, or there are gaps, or there are duplicates. This is a very common thing, is you have the same fact that shows up several times in your knowledge graph. Okay. Or you have labeled nodes that are synonymous, which is redundant. Or you have inverse. So you have a dog has part legs, and then some people also add legs are a part of a dog. So they have the same fact, but reversed because it's easier to index that way. Okay. But this is a huge headache because that means you have twice as many things to review and double check without tools. Okay. So there are a range of things like this, a range of traps like this that people fall into. Okay. So these are some really basic ones. For me, the most important trap is that people work with labels and they don't define them, right? So each of a node is supposed to represent a concept. Okay. If we put a label on it, then we have a string. We know that it's distinct from other nodes with different labels. Okay. But we don't give our systems information, most of the time, don't give our systems the information it needs to understand, well, what is meant with that symbol, with that label. Okay, so we end up with things like we have a node for cars and we have a node for automobiles. And then we have a separate node for jalopies or for roadsters they're all different, even though in many cases they're either the same thing or very close.
Okay. So I have a follow on this question, all right?
Sure.
Let's say a graph actually has, a separate node for a Roadster or a Tesla and so on and so forth, right? What does that mean? Or how does that impact the final output? Or what gets impacted eventually when you have these traps present? I guess the question is then, why would you want to solve for these in the first place? Or what's the downstream impact that you're looking at when you have these issues and gaps?
So what this does is it bloats the graph. Okay, so there's a lot, it makes it much more difficult to evaluate and to track and to validate. And when you have the same node in different, for example, you have a node for automobile and a node for car. Okay, and as you create your graph, you have more information for car and more information for automobile from different sources. But then you don't see that they are the same thing and that they should be merged. So if you do a query on car, you get one set of responses, or a query on automobile, you get a totally different set of responses, whether you use an LLM, a regular search engine, anything like that. So you're teaching your system that they're two separate things, okay? Which means you'll get different responses. So I actually did a study with Google about this. I went into Google Shopping and said, okay, let's see if we can buy a dog. So you do a query for dog, nothing shows up. But if you do a query for canine, or for barker, or for pooch, or for puppy, you get totally different results. This is not the behavior we want. We as humans want the system to give us similar responses for similar things. If I put in a query for cars, I want to get something very similar to if I put in for automobiles.
Correct.
Okay? So this is frustrating for the user, but it's actually disastrous for a data scientist. Because if a data scientist is drawing conclusions based on one query instead of the other query, then they'll have a biased view of the data. And they'll have a subset. They'll have a subset of the data to work with, and it won't be representative of the data that is available. Which means that most of what we get from data science using these kinds of queries is totally unreliable.
But now, you again mentioned a specific term here, which was validating knowledge graph, or the validation itself becomes tricky. Right? It's a very difficult thing to wrap your head around. Why would you want to validate a graph that has been created from, your source of your let's say documents, policies, procedures, and so on? Why is validation important? And that seems like a very tricky, humongous, human-led task, or is it all automated? Which is
It's
like
always been human led. This is why I built a team at LinkedIn to do exactly that. The question of why is a very simple one. The software that we use and the processes that we use to build knowledge graphs aren't 100% reliable. And we don't know where they're less reliable and where they're more reliable. We simply don't know. So as we build them, and as we build them at scale, we build resources that have more and more problematic parts. Okay. Now, why? Would you build a database with incorrect information?
That doesn't make any sense.
It doesn't make any sense. A knowledge graph is a kind of database. We use it in the same way as a foundation for other things that we want to do with it, for the conclusions that we want to draw. Okay. If you built a database wholly automatically, we would call that synthetic data, which is fine and is useful for several things, but it's not useful for making decisions about what you should do to make your company grow.
Correct.
And the same is the case for knowledge graphs, right? And we can build it automatically. That graph built automatically, however unreliable it is useful for some things, for testing processes, for a range of other things. But it's just not going to be reliable for reasoning, for drawing, conclusions that you can bank on, for you being used as a single source of truth.
Mike, in your years of experience of working in the industry, championing for knowledge architecture, knowledge graphs, we do see a very prevalent notion today, which is, why do you even need a human in the loop at all? So upstream. People have eventually pushed all the human in the loop downstream, which is the agent is doing something or the AI is doing something, can be verified.
And the human cleans up the mess.
Verify, right? But what you are arguing is shift the human left or shift the human far up in the value chain.
Possible.
Right?
Yes.
Yes,
so
that's
the
possible, but it's very counterintuitive.
The human's impact is multiplied by the agents, right? Because if we have the multipliers first, then the burden on the humans increases exponentially.
Yes, it does make sense. What I'm trying to understand is, in your experience, have people started to buy into that? Because the hype says, the hype has sort of pushed the industry in a very different direction right now, which is, have
agents
some
can
human
do
in the
everything.
loop and age and, yes. But what you're saying is, build the foundation first. And that too seems like a very manual effort right now. How do people receive this?
It used to be manual.
Okay.
But now there are many tools for building that. We mentioned a minute ago that we have all these tools for building knowledge graphs. I want to push back a little bit on how you described how things are going now. Now what I see is a movement toward describing skills for agents. So we're more and more investing in the foundation before we get the multiplying effect of the agent. Right? So we're going back a higher level of abstraction, saying, look, this is how this skill works, and this is what I want you to apply. That's, in my mind, parallel to what we do with knowledge graphs, which is, this is how we think about the world, and this is what we want you to apply. So I think what converging in this sense, in a focus on, I think you called it a focus on foundations.
Right. Okay. So that's a very interesting point that you brought up, because there's also a growing notion that all I need is a bunch of MD files. I need a, skills MD file. I need a copywriting MD file. I need a QA MD file, and then my life should work as promised, right? But that's also not the case, unfortunately.
Correct.
Right?
It's also not the
So
case.
what are people missing there in that case? What do you think is
what I think is missing is MD files provide sparse clues for the AI to guess at what you mean. So a key observation is a long-standing one is if you phrase the same prompt in different ways, you get different responses. Okay? So that for me is a clue that the system is just guessing at what you need. Okay? It can't resolve them into, these two prompts mean the same thing. Let me give you the same response as I would usually give for that prompt. Our systems can't do that yet. So they're responding in a much more granular way than we need them to respond. It's just like the search query. If you're looking for dogs or pooches or automobiles or Teslas or whatever it is, we get a response to the very, very granular, specific synonym or spelling that was chosen, and not to the more abstract or aggregated concept.
Okay, this is very interesting. Now, again, going back, because you sort of worked in this space for so long, when transformers were introduced and when these models came out, GPT-3, GPT-2, and so on, right? When was the first time you realized that it's not the model, that the model has certain glass ceiling to itself? Because for a lot of people, that's the inflection point, right? When did that happen for you, and how did that happen? Also, I think it'd be very interesting to learn about that.
So the two observations that I saw immediately. One is, let's look at the input. How is this trained? It's trained on strings. Okay, so it can't go beyond strings if it's only trained on strings. Okay, and then we see that reflected in the fact that different phrasings of the prompt lead to wildly different responses. Okay, so it's working at the string level. And for that, language models are really fabulous. So if there's some sort of string manipulation task or task that can be translated into string manipulation, then they work very, very, very well. Okay, but as soon as you want to do something like, okay, extract for me all of the things that are examples of dogs, and then it will fall flat on its face.
So, Mike, this was like for GPT-3, it would have been just strings. What do you think of models today where they've been trained on images and audio and things like that?
Oh, that's a whole different story. So the multimodal models, start to add meaning or concepts because they're attaching the strings to different, let's say, images. Okay, and the image is a kind of a snapshot, as it were. Maybe not a good metaphor, but an encapsulation of the concept. So we have, with these multimodal models, a way to disambiguate the strings in different contexts. Okay, and as you're hinting at, Josh, I would say that's a huge step up. So now we're not working with strings anymore. Now we have these initial versions of concepts, which don't use strings as the unit, right? And now we can add to that by making them more explicit and tying down the things that we're sure of to feed those to the model and help guide the model. So in the past, this is something Vivek was mentioning earlier, we had people doing on a huge scale. I mean, I organized this at LinkedIn, is tagging, okay? So you have an input and you tag it. You have an image and you tag it. But when we do that, we don't give the systems the machinery they need to double check the tags. We don't give it reasons. This is why I think this is a cat, okay? Or this is why I think this job is actually for a software engineer. We don't do that because we don't have the concepts available to feed to the system so that it will have the machinery it needs to double check, right? So what you're talking about, the multimodal things, are some associations that start to build these concepts.
Yeah. So I think it like even ties back to what you were talking about earlier about, I think you said dog and canine, right? And
Yes,
then you know that dogs have a certain set of characteristics and a
correct.
canine has a similar set of characteristics. So what would be the solution for, like, do we use a neural approach to, figure out, okay, these things are similar? Do we use some kind of like, reasoning or like maybe a more symbolic reasoning where we say that, hey, the dog has 10 properties and a canine has 20 properties, and maybe a dog is a subset of a canine or something like that. Like,
Yes,
is that, what are some solutions, like, how do we deal with this ambiguity since we're dealing with, the same thing in a multimodal setting? I think the question is like, how do we, bring it all together and have this resolution, as it were, of those instances that you spoke about where data is clearly wrong. Like, people are tagging things wrong. You're
they
seeing
do.
that searches, you don't pull up the same thing. A neural model could get it, for whatever reason, well, like something we don't understand. Maybe the features that they sampled using their autoencoders could be off. So like how do we deal with that? Like how, like both human and machine are failing. So how do we,
Exactly. That's an
good
that's
practice?
a wonderful summary. So the systems we have, both the humans and the machines are failing. And this is what's, in my way of thinking, pushing the neurosymbolic approaches to the forefront, where we try to use the best of both. So we can build a more explicit feature space and then use neural methods to exploit it. When we talk about a feature space, we're talking now more than just strings, the presence or absence of strings, which is a very weak and feature space to start from. Okay, I think you got it. If we're talking about, foundational features that we can combine in different ways to create concepts, okay, and have strings attached to those and have images attached to the concepts, then we have another level of abstraction or aggregation that we can use as a more robust foundation for building neural systems. Right? I
So
would say it's the big change here is in the way we build our features. Basically, we take it up a level of abstraction so we don't get lost in the granularity.
so in some sense, we need to change the space, is what
That's,
I'm
that's how I
hearing,
look at
right?
it. Yes. Yes. That's how I look at
It
it.
can't be strings or pixels or, you know, audio waves, it has to be conceptual. It has to be like at a concept space, and so to speak, right?
Yes. Not so to speak. Exactly. That's how I would phrase it. Okay. So one of the benefits we get from that is that by making this shift, we set aside or deal with a huge amount of variance, of noise in the data. Okay. And that's one of the big benefits of moving up a level of abstraction, is that the feature space is smaller, the concept space is smaller and more consistent. So we need literally thousands of times less data to do the same sort of things. Right?
But yeah.
So we're talking about a kind of compression, right? We're compressing all this variation of data into concepts, single concepts. It's a huge amount of compression. We're talking about tens of thousands of times more compressed.
But we also need the links
Thanks.
back to the many, variations as well, because if we need neural and symbolic to
For
work.
communicating with this system, right? So the experience I have with it is at LinkedIn. For any particular concept or a job or a skill, we could find literally thousands of synonyms. Okay, and this is what my team was focused on, moving up a level of abstraction so that the algorithms did not have to deal with 150 million job titles. They only had to deal with 5,000 job titles, because there were so many synonyms. And 5,000 job titles, that one makes it possible for humans to review and curate. And two, it eliminates so much of the variance that plague machine learning systems, that we got much better results.
That's 1:30,000. That's massive.
Yeah,
That's
massive.
Yeah,
Massive. Yeah.
massive.
Well,
Yeah.
think of it. If you think of 1,000 synonyms and 30 languages, then there you go. That's your 30,000 right there. So LinkedIn can match your resume in English to a job posting in Hindi and do it well, right? Because we push everything up a layer of abstraction and say, here's this concept and here's that concept.
That's also sort of brings me, Mike, to a usual struggle or a common struggle for a lot of AI teams, because of which they tend to refrain from picking knowledge graph in their AI stack is, oh my God, managing a graph is a big thing. It's a big headache, right? You have seen a different level of scale when it comes to building, not just building, but building, managing, scaling these solutions, these graph-based approaches, right?
Mm-hmm. Yeah.
What things should folks watch out for as the graph starts to expand from, let's say, a few hundred, a few thousand nodes to say a few million nodes to say a few multi-million nodes, right? Like what like what does that journey look like? Yeah.
Okay, that's a big question. Lots of unpacking to do. One of the things that I think is probably the first thing I would say would be to split the graph. So Joshua was saying a minute ago, we need the links back to the data. In our case, we need the links between the concepts and the strings. Okay? That link can be a separate graph or a separate database. Okay? So we can focus on certain kinds of reasoning only on the concepts or the categories and the relations between them. Okay? So that partition already makes the process a lot easier. So we had teams of people looking for synonyms because that made our system more robust. Okay? And they worked on this one collection here of synonyms. Okay, double checking that the synonyms were accurate and not leading us to problems. But we had a different team that was working on the core categories and the kinds of relations between them to make those richer and allow for different kinds of reasoning. They're very separate and they're very different scales too of things. So that kind of splitting the problem up into different parts is really essential, I would say, for this. Still, I want to remind you that, as we said a minute ago, the scale is enormously smaller than managing trillions of words of training data, right? Getting into a million node graph is very difficult to do. They're usually much, much smaller. Okay, so that leads to the next thing to focus on, which is priorities. Which concepts are important for your business, right? Because there's a long tail. If you can focus only on the head, then you get the impact without the work.
Mm-hmm.
So prioritization is really key for that. This is something we saw practically monthly. We go and see, okay, here are the titles all the titles in the database. Let's sort them by frequency and take the head and make sure we can do a very good job on the head. And when we got to that point, we started looking, okay, are there easy ones to do in the tail? Can we map them to concepts from the head to increase our coverage? Okay.
Mm-hmm.
So there were things like this that we could do to divide up the work and make it more effective. And then on top of that, so at LinkedIn, we didn't have much in the way of tooling. We did all of the work very manually. And it's in response to this experience that makes me at Hypergraph want to build more robust and more informative tools.
Makes sense. I do have a follow-on on that, Mike, which is when you talk about as part of the whole managing and building process, right? A thing that you have said in the past is it's not about the size of the graph, it's about the relations in the graph. It's something that we also think a lot and focus a lot of our time and energy on is number of nodes is far secondary than the triples or the relationship between those nodes. One, explain why. That's the first question. And, how does that start impacting? Like, how would a sparse graph underperform, or let's say, underperform a more dense graph?
So when I really like to focus on the relations in the graph, because I think they're very important. One way you can think of it is for each relation type, you have an extra dimension, an extra method for comparing nodes and for defining nodes, right? So the subgraph attached to a node is, for all intents and purposes, the definition of that node. So if you only have one kind of relationship, it's a very poor or impoverished definition. If you have 10 different kinds of relations attached to a node, then you have a much richer definition and more for the system to work with. Okay, so this is where one of the places where my emphasis on relations comes from. You may have noticed this. I've done interviews and written pieces on relation resolution. Okay, a big problem that many people deal with is you have duplicate nodes because the labels are slightly different, or we don't have sufficient information to resolve them. Okay, so this entity resolution is super important, and it's been shown across many, many, many domains. We have to do the same thing for relations, especially now that we're building them automatically, right? Because we have this redundancy, which makes it harder to maintain, and it misguides the system to go in different directions when they should be looking at the same things. On top of that, the vocabulary of relations that we use, the optimal vocabulary that we use, is a few dozen, okay, which makes it much tractable for humans. Okay, it makes it possible for us to curate and monitor and do quality assurance, right? So we're compressing the information in a way that makes it both human tractable for really high quality. But by combining these relations in a range of different ways with different values, we can create literally millions of concepts from these components. So we get the best of both. We get the scale because we can combine them, but we get the tractability because the core relations are a small set, relatively small set.
Makes sense. Makes sense.
Okay.
Now, like another, we see a lot of new teams new to the world of graphs and ontologies and so on, trying to evaluate this sort of fit it into their stack and so on and so forth. Like, what are some of the questions that they should, or any specific framework that you would recommend as they, or mistakes that they should really watch out for before they start investing, time and energy in building their enterprise knowledge graph? Because the notion, of course, today is, let's take a LLM, let's throw it at the data, and let's create a knowledge graph, right? That's the fast track approach, of course, right? But what would be some interest, some realistic, milestones that they would set as they try to, operationalize or put this into production? Right? Yeah.
So I think that takes us back to something we mentioned before is priorities. So building a knowledge graph is a modeling activity. We want to make a qualitative model of the domain that we're interested in. Okay. It's not a text processing. It's not a text processing operation. It's a modeling. So how does your organization think about this domain where it operates? And this is what we try to capture in the knowledge graph. So your organization thinks that these are important entities and these are important characteristics or properties, and these are important events. So as soon as we can identify the most important things, we can start modeling them and build out from there. So the first thing is it's not a text processing operation. It's a domain modeling operation. Okay. The second is, why not use LLMs? But the LLMs have to have enough resources in terms of background knowledge or skills to do a good job. Just asking an LLM, oh, build me an ontology, it will give you something sketchy that kind of almost looks like an ontology, but it would be pretty bad and it won't scale. Why is that? We didn't tell it what we think the relations mean. So it's not going to be consistent. We didn't tell it what we think a category is or a concept is. We didn't tell it how to organize them and what kinds of things to watch out for. Okay. But once we do that, I have files of definitions of relationships for knowledge graphs. And once you feed those into the LLM, they start doing a much, much better job.
I guess, the most important takeaway, Mike, for me is the very first point, which is most organizations, small, mid-market enterprise, it's looked as in the whole process of sort of building a knowledge foundation or a knowledge graph is done by engineers and not domain experts. Right, to your point, which is it's a data modeling.
No, it's not
project.
a domain. It's not a data modeling project.
Sorry.
But this is what our friends, the engineers, know how to do. This is how they've been trained.
Yeah.
So of course, this has got to be their first response.
Right.
Mm-hmm.
Right. And
I think this is how my team added value, because we were not engineers. We added complementary skills to what the engineers could do. And together we could do much more.
It's out again.
So Vivek, something we talked about before that I think would be useful to raise here is, since we were talking about the relations or the predicates and how important they are, I like to tell a story about meeting the director of a big pharma company at a conference.
Yes.
And asking him, oh yeah, how's it going? How are you using your knowledge graph? And is it a good one? Is it a big one? And he stopped and he said, yeah, it's really very big, but we're not finding it useful at all. We put in a query and everything is related to everything. It's just we're overwhelmed with results. And I said, wait, stop. You're using a knowledge graph and it's not useful? How can that be? So I peppered him with questions and I squeezed him, and I didn't let him leave until we could figure out what was going on. And it turns out that they had overinvested in a particular kind of relation. Okay. And that's this associated with relation or related to relation. Okay. So that what happened was, every time they put a query into the system, they had very robust query expansion, actually too robust, because everything was in one way or another associated with everything else. Okay. And that made me understand that it's not over-reliance on one kind of relation is a really big problem. And over-reliance on this uninformative kind of relation is killer. So they spent millions of dollars building up these associated with relations, and it ended up undermining the effectiveness of the system.
And that's
Actually,
something which was figured out from a knowledge graph audit of sorts.
Yes, it was a knowledge graph audit. Yeah. An informal one with a cup of coffee in the hallway, but it was still a kind of audit. And this is the kind of thing that I'm trying to automate. Okay, that we're trying to automate with the tooling we're building now is you push in your graph, and we can see, wait a minute, you only have 3 kinds of relations for this complex sort of domain. That's not going to meet your needs. Okay.
Nice. Right.
And I think, yes. And a similar problem that I saw with another client was they had, I think it was a protein database or something like that. But they had invested a lot in making the link between what was in the knowledge graph and what was seen in the literature. So they had this relation mentioned in. Cool. So this protein is mentioned in this study, in that study. Oh yeah, and this study has an author, and this study was published in this other place. And it turned into a librarian's knowledge graph.
Yeah.
instead of a protein researcher's knowledge graph.
Right.
Right. But they had no way of noticing that.
Right. And before you know, you have so much bloat, which is just dragging you down
Yes.
from a performance point of
The
view. And this is
overhead.
too much
And then
noise.
there's too much noise. Exactly. So that undermines the reasoning about proteins, which is what their main goal was. Yeah.
Main goal was, yes.
So that one, I thought that was a sad knowledge graph.
I think we should do a separate episode on knowledge graph audits altogether. I'm sure there will be, so many interesting patterns that you would have seen, right? Where, and like, again, so many learnings for people who have started to finally adopt this extremely powerful technology. Yeah.
So this
Awesome.
is what over the last year or so, this is where most of our clients have shown up, is saying, okay, we have a knowledge graph. We know it's important. Are we doing it right? Okay. How can we improve it? How can we scale it up? And that involves an audit. So we go through, do an audit and say, okay, these things are working well and these things are not. And here's how you can improve them. And I think it's fun work.
It absolutely is. I mean, we have so much fun building some of these cells, right? And sort of, navigating through it with our customers is just, and then once it gets activated or once sort of, gets utilized to build an actual data product, which gets consumed by an application, all of that stuff is, and then seeing reliability baked into some of those applications, problems like traceability getting solved and so on, right? I think like, those are real benefits, which people are, which obviously enterprises haven't seen for a while now, unfortunately.
Exactly.
Right?
Yes.
Yeah. But I think it's also the narrative that you can I think people feel very comfortable to push the human downstream to validate versus having the human validate the graph or validate the knowledge foundation and not the outputs, right? I think that's a very big takeaway for me personally. Yeah.
Yeah, the human skills have to move upstream, right? To design the strategies and design the schemas and design and identify the priorities and do the domain modeling that give you the guidelines and the guardrails for the graph. Right?
Perfect. All right, Mike, one last thing. One question that we ask all our speakers or our guests is, one thing you would change about how enterprises do this, and it actually happens tomorrow morning. What would that be?
Bring in decision makers with varied backgrounds and not just engineers. That's it. Engineers do marvelous things with the things they know, but there are many things in this domain that they don't. Our emphasis has moved into psychology, cognitive psychology, cognitive science. And engineers don't have training in that. So how are they going to deal with reasoning in automated systems? They can't. They have no training to deal with that. How are they going to process language and all the complexities of language? They don't have training in that. So we need more diverse teams.
That's a fantastic message, Mike. Thank you so much once again. For our audience, Mike, where can people find you?
All my publications come out on LinkedIn. I'm easy to find there. And periodically get out to do interviews and present at conferences. So I'm here.
Once again, awesome. Thank you, Mike.
Thank you very much.
Your website is hypergraph.ai, is HYP.
.ai, correct.
That's perfect.
That's right.
We'll put that in the show notes for you. Right. Once again, thank you so much for taking the time, Mike. Really appreciate. Love the conversation.
And thanks for having me. I appreciate the discussion.
Thanks, Mike.